User Datagram Protocol, or UDP. UDP is one of the core members of the Internet Protocol Suite or stack, the stack set of network protocols used for the Internet. With UDP, computer applications can send messages, in this case referred to as datagrams, to other hosts on the Internet Protocol network without prior communications to set up special transmission channels or data paths. The protocol was designed by David Reed in 1980 and formally defined in RFC 768. UDP uses a simple transmission model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes any unreliability of the underlying network protocol to the user's program. As this is normally IP over unreliable media, there is no guarantee of delivery, ordering, or duplicate protection. UDP provides checksums for data integrity and port numbers for addressing different functions at the source and destination of the datagram. UDP is suitable for purposes where error checking and correction is either not necessary or performed in the application, avoiding the overhead of such processing at the network interface level. Time-sensitive applications often use UDP because dropping packets is preferable to waiting for delayed packets, which may not be an option in real-time system. Such kind of software or such kind of application services are voice over IP, IPTV, or similar things. If error correction facilities are needed at the network interface level, an application may use the Transmission Control Protocol or Stream Control Transmission Protocol, SCTP, which are designed for this purpose. A number of UDP's attributes make it especially suited for certain applications. UDP is transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol. UDP provides datagrams suitable for modeling other protocols such as in IP tunneling or remote procedure call and the network file system. It is simple, suitable for bootstrapping or other purposes without a full protocol stack, such as the DHCP and Trivial File Transfer Protocol, TFTP. It is stateless, which is suitable for very large numbers of clients, such as in streaming media applications, for example, IPTV. The lack of retransmission delays makes UDP suitable for real-time applications such as voice over IP, online games, and many protocols built on top of the real-time streaming protocol, or RTSP. UDP works well in unidirectional communication, suitable for broadcast information such as in many kinds of service discovery and shared information such as broadcast time and Routing Information Protocol, or RIP. UDP applications use datagram sockets to establish host-to-host communications. An application binds a socket to its endpoint of data transmission, which is a combination of an IP address and a service port. A port is a software structure that is identified by the port number, a 16-bit integer value allowing for port numbers between 0 and 65,535. Port 0 is reserved, but is a permissible source port value if the sending process does not expect messages in response. The Internet Assigned Numbers Authority has divided port numbers into 3 ranges. Port numbers from 0 through 1023 are used for common, well-known services. On Unix-like operating systems, using one of these ports require super-user operating permission. Port numbers from 1024 through 49151 are the registered ports used for IANA registered services. Ports starting from 49,152 through 65,535 are dynamic ports that are not officially designated for any specific service and can be used for any purpose. They are also used ephemeral ports from which software running on a host may randomly choose a port in order to define itself. In effect, they are used as temporary ports primarily by clients when communicating with servers. UDP is a minimal message-oriented transport layer protocol that is documented in IETF RFC 768. UDP provides no guarantees to the upper layer protocol for message delivery, and the UDP protocol layer retains no state of UDP messages once sent. For the reason, UDP is sometimes referred to as an unreliable datagram protocol. UDP provides application multiplexing and integrity verification of the header and the payload. If transmission reliability is desired, it must be implemented in the user's application. The UDP header consists of 4 fields, each of which 2 bytes or 16 bits. The use of the fields checksum and source port is optional in IPv4. In IPv6, only the source port is an optional. So let's discuss each field of the UDP header. Source port number. This field identifies the sender's port when meaningful and should be assumed to be the port to reply to if needed. If not used, then it should be 0. If the source host is the client, the port number is likely to be an ephemeral port number. If the source host is the server, the port number is likely to be a well-known port number, not a field destination port number. This field identifies the receiver's port and is required, similar to source port number. If the client is the destination host, then the port number will likely be an ephemeral port number, and if the destination host is the server, then the port number will likely be a well-known port number. Length. A field that specifies the length in bytes of the entire datagram, header and data. The minimum length is 8 bytes, since that's the length of the header. The field size set a theoretical limit of 65,535 bytes. It means 8-byte header and rest of the bytes of data. The practical limit of the data length, which is imposed by the underlying IPv4 protocol, is 65,507 bytes. In IPv6 jumbograms, it is possible to have UDP packets of size greater than 65,535 bytes. This allows for a maximum length value of 4,294,967,295 bytes, or 2 raised to 32 minus 1. The checksum. The checksum field is used for error checking of the header and data. If no checksum is generated by the transmitter, the field uses the value all zeros. This field is not optional for IPv6. Checksum is the 16 bits ones complement of the ones sum of the pseudo header of information from the IP header. In other words, all 16-bit words are summed using ones complement arithmetic. The sum is then once complemented to yield the value of the UDP checksum field. If the checksum calculation results in the value 0, it should be sent as the ones complement. The difference between IPv4 and IPv6 is in the data used to compute the checksum. When UDP runs over IPv4, the checksum is computed using a pseudo header that contains some of the same information from the real IPv4 header. The pseudo header is not a real IPv4 header used to send an IP packet. It is used only for the checksum calculation. The source and destination addresses are those in IPv4 header. The protocol is that for UDP 17 or 0x11. The UDP length field is the length of the UDP header and data. UDP checksum computation is optional for IPv4. If a checksum is not used, it should be set to the value 0. Lacking reliability, UDP applications must generally be willing to accept some loss, errors, or duplications. Some applications, such as TFTP, it's a trivial file transfer protocol, may add rudimentary reliability mechanism into the application layer as needed. Most often, UDP applications do not employ reliability mechanism and may even be hindered by them. Streaming media, real-time multiplayer games, and voice over IP are examples of applications that often use UDP. In these particular applications, loss of packets is not usually the fatal problem. If an application requires a high degree of reliability, a protocol such as the transmission control protocol may be used instead. Potentially, more seriously, unlike TCP, UDP-based applications don't necessarily have good congestion avoidance and control mechanisms. Congestion insensitive UDP applications that consume a large fraction of available bandwidth could endanger the stability of the Internet, as they frequently give a bandwidth load that is inelastic. Network-based mechanisms have been proposed to minimize potential congestion collapse effects of uncontrolled, high-rate UDP traffic loads. Network-based elements such as routers using packet queuing and dropping techniques are often the only tool available to slow down excessive UDP traffic. The Datagram Congestion Control Protocol, or DCCP, is being designed as a partial solution to this potential problem by adding the end host TCP-friendly congestion control behavior to high-rate UDP streams such as streaming media. Numerous key Internet applications use UDP, including the Domain Name System, or DNS, where queries must be fast and only consist of a single request followed by a single reply packet. The Simple Network Management Protocol, or SNMP, the Routing Information Protocol, or RIP, and the Dynamic Host Configuration Protocol, or DHCP. Voice and video traffic is generally transmitted using UDP. Real-time video and audio systems streaming protocols are designed to handle accessional lost packets, so only slight degradation in quality occurs, rather than large delays if lost packets were retransmitted. Because both TCP and UDP run over the same network, many businesses are finding that the recent increase in UDP traffic from these real-time applications is hindering the performance of applications using TCP, such as point-of-sale, accounting, and database systems. When TCP detects packet loss, it will throttle back its data rate usage. Since both real-time and business applications are important to businesses, developing quality of service solutions is seen as crucial by some. Now let's compare UDP and TCP protocols. They are both transport layer protocols. Okay, transmission control protocol is a connection-oriented protocol, which means that it requires handshaking to set up end-to-end communications. Once a connection is set up, user data may be sent bidirectionally over the connection. Okay, TCP is reliable. TCP manages message acknowledgement, retransmission, and timeout. Multiple attempts to deliver the message are made. If it gets lost along the way, the server will request the lost part. In TCP, there is either no missing data or, in case of multiple timeouts, the connection is dropped. Ordered. If two messages are sent over a connection in sequence, the first message will reach the receiving application first. When data segments arrive in the wrong order, TCP buffers delay the out-of-order data until all data can be properly reordered and delivered to the application. Heavyweight. It means TCP requires 3 packets to set up a socket connection before any user data can be sent. TCP handles reliability and congestion control. Streaming. Data is read as a byte stream. No distinguishing indicators are transmitted to signal message boundaries. Let's discuss the UDP. UDP is a simpler message-based connectionless protocol. Connectionless protocol do not set up a dedicated end-to-end connection. Communication is achieved by transmitting information in one direction from source to destination without verifying the readiness or state of the receiver. However, one primary benefit of UDP over TCP is the application to Voice over Internet Protocol, where latency and jitter are the primary concerns. It is assumed in Voice over IP UDP that the end users provide any necessary real-time confirmation that the message has been received. Unlike TCP, UDP is unreliable. When a message is sent, it can be known if it will reach its destination. It cannot. It could get lost along the way. There is no concept of acknowledgement, retransmission, or timeout. Again, unlike the TCP, UDP is not ordered. It means if two messages are sent to the same recipient, the order in which they arrive cannot be predicted. Lightweight. There is no ordering of messages, no tracking connections, and so on. It is a smaller transport layer designed on top of IP. Datagrams. Packets are sent individually and are checked for integrity only if they arrive. Packets have definite boundaries which are honored upon receipt, meaning the read operation at the receiver socket will yield an entire message as it was originally sent. And the last one, it is UDP, unlike TCP, is no congestion control. UDP itself does not avoid congestion, and it's possible for high bandwidth applications to trigger congestion collapse unless they implement congestion control measures at the application layer.